Good afternoon, class. This is chapter 2 review, limits and derivatives. So in this chapter, we're going to go over the tangent and velocity problem, limits of a function, calculating limits using the limit laws, precise definition of a limit, continuity, limits at infinity, derivatives and rates of change, the derivative as a function. So first and foremost, the definition of the limit. The limit exists if the one-sided limits are identical. In other words, the limit of f of x as x approaches a from the left and the limit of f of x as x approaches a from the right are the same. In that case, the limit exists. So when we look at this graph, which contains three parts, we notice as x approaches a, the limit is L in all cases. In this case, also f of a equals L, which makes it continuous at a. In this case, f of a is a different value, b, which makes it discontinuous at a. And in this case, f of a is just missing, we don't have it done. So those are the differences. And the definition of a continuity is that if the limit exists and it's equal to f of a. When you take a limit of f of x as x approaches a, or a from the left or a from the right, we end up with positive or negative infinity. In that case, we say the VA or vertical asymptote has an equation of x equals a. If you take a limit as x approaches negative or positive infinity and we end up with some number, we say y equals L is the horizontal asymptote. Now, when we look at this graph, we are interested in finding the limit of f of x as x approaches 2 from the left, 2 from the right, and finally 2. So here's number 2. From the left of 2, we are in this branch. We end up here with 3 being the y coordinate. On the right side, we're moving this way, and 1 is the y coordinate. Since they are not identical, the limit does not exist. Now, what is f of 2? You look at this dot, which has the y coordinate 3. That's the answer, 3. What is limit of f of x as x approaches 4? From both sides, we are moving towards this point, having the y coordinate 4. What is f of 4? I don't know. It's not given. It's undefined. So again, we want to distinguish among those. We have this function. We are interested in finding the limit of r of x as x approaches 2. Here's number 2 on both sides. We're going down to negative infinity. 5, we are coming towards 5 from the left and right. It blows up to positive infinity. However, at negative 3, it depends on the left. You're going towards negative infinity, and on the right side, positive infinity, in which case all of them tell us the VA, vertical asymptotes, x equals negative 3, x equals 2, x equals 5. Those are the equations. All right, let's look at these limits. When we plug in, we get 0 over 0, in which case you have to use your techniques. In this case, the technique is the conjugate of the numerator. So this is like a minus b. This is like a plus b. The result is a squared minus b squared. So the first one comes out as x plus 4. The next one is negative 4, because minus 2 squared. 4 and negative 4 cancel each other. We end up with x in the numerator, cancels out the x in the denominator. If we plug in, we get square root of 4, which is 2, and 2, 4, 1 over 4. Now, numbers 29 and 30, I want you to see the following. Both of them end up being negative 1 over 0. Now, when we have any number, positive or negative, both sides are the same. So when x approaches negative 3 from the right, and when you plug this in, whether it becomes negative 1, negative 1.1, or negative 0.99 is not important, because both sides basically have the same sign, namely negative. The same thing happens here. However, 0 is the only number that has different signs on both sides. Therefore, when we look at that, we have to pay attention to this. And negative 3 from the right, something like negative 2.9, even you can pick up an example, negative 2.9, even negative 2, because we are interested in the sign. When we add it to 3, the answer is positive 0.1. So it's negative 1 over 0 from the right. And why is this important? Because negative over positive is negative, and the answer is negative infinity. However, in this case, negative 3 from the left, an example of that would be negative 3.1, and plus 3 becomes negative 0.1, which means a 0 from the left. And negative over negative is positive, therefore the answer is positive infinity. And that's the idea. Anytime you have a rational expression, the best course of action is to factor the top and the bottom. However, if you didn't, you end up with 0 over 0. And because x approaches 4, you should have a factor of x minus 4 in the denominator. We do the factoring. X minus 4 drops. And now if we replace the x with 4, we get 4 over 5. Same thing happens here, 0 over 0. Therefore, we multiply by its conjugate. Again, a minus b times a plus b results in a squared, which means 1 plus h comes out, minus 1 squared, which is 1. 1 and negative 1 cancel each other. Also, h cancels out the h. We put 1 here, and when we plug in 0, we get square root of 1, which is 1, and 1 is 2. 1/2 is the final answer. Limit laws, in short, says if the limit of f of x as x approaches a and g of x as x approaches a do exist, then the limit of the sum is the sum of the limits. The limit of the difference is the difference of limits, so on and so forth. However, direct substitution property says if you have a continuous function at a, then we know the limit of f of x as x approaches a equals f of a. Simply plug in and observe. Function with the direct substitution property are called continuous at a. This is the definition of a one-sided limit. Everybody remembers that. And I'm going to add this squeeze theorem. If g of x is between f and h, it's sandwiched between the two. When x is near a, except possibly at a, and this limit of the left side, f of x as x approaches a, and the right side, the limit of h of x as x approaches a, both of them result in L, then the middle one must give you the same limit. The limit of g of x as x approaches a must be the same. So we are going to use that. Over here, we just plug in. It's important to know that you plug in and you observe. When you plug in number 6, this becomes 0, everybody, and this becomes 3. This is 6 squared root 36 minus 7 times 6 is 42 plus 12. So the numerator is 3, and the denominator adds up to number 6, which is therefore 1/2. In other words, plug in, it works, we are done. If you plug in, you get 0 over 0. You're dealing with what's called a complex fraction. And the best course of action is to multiply by LCD. In the numerator, you have two fractions. The LCD is 3x. You multiply and divide by it. If you multiply this one by 1/3, you get x. If you multiply it by 1/x, you get 3. So you get x minus 3. The denominator, you don't touch it. You keep it as a product. These two cancel each other. And at this point, you plug in and you get 1/9. We want to evaluate the following limits. The limit of f of x plus 5 g of x as x approaches -2. So first we use the limit laws. We cut them into two pieces and we take the 5 out. And now we have to calculate the limit for f of x as x approaches -2. It's the red function. And here's -2 from the left and right. Left, we are here. Right, you are here. In both cases, we end up with number 1. So that's number 1. The g function is the blue function. And as we go to -2, here's number -2 from the right and left. Both of them, they take us here, giving us the y coordinate of -1. And so this would become 1 plus 5 times -1, which is -4. What about the limit of f of x times g of x as x approaches 1, which is the product of the two? So we're going to look at this piece, and we're going to look at this piece. There are two ways to look at it. I'm going to quickly look at both ways. If you look at this one, limit of f of x as x approaches 1, here's number 1 on the x-axis, left side and right side. So left side, we are here, right side, we are here. In both cases, we end up here. We are moving towards that point, which has a y coordinate 2. But for g of x, the blue function, the limit doesn't exist because the limit on the left takes us here, which is -2. On the right, takes us to the whole, which is -1. So this doesn't exist. So this is 2. This doesn't exist because they are not identical. That's the reason. Therefore, this does not exist either. The limit of f of x times g of x as x approaches 1 does not exist. Another way you can do that, you can find the limit of this as x approaches 1 from the left and as x approaches 1 from the right. So 1 from the left, it's simply put 2 times -2, which is -4. Now, if you take this limit as x approaches 1 from the right, this one is 2. Right and left makes no difference. This one is -1, and therefore -2. Since the two are not identical, the limit doesn't exist. Either you do it this way or you look at this process, makes no difference. We are interested in finding the limit of f of x over g of x as x approaches 2. So when we look at number 2, in this case, f of x is approaching this value. So the limit exists, and whatever you read here may be 1.4. G of x goes to 0, and because of that, it doesn't exist. The denominator approaches 0, while the numerator approaches a non-zero number. As I mentioned, the Squeeze theorem basically says if this one and this one, we can find the limit, the one that is squeezed in between has the same limit. So in this case, we don't know what g of x is, but the left side is 2x. So let's take a limit of 2x as x approaches 1, because we are interested in finding the limit of g of x as x approaches 1. So 2x gives us 2. How about this piece? The limit of x to the power of 4 minus x squared plus 2 as x approaches 1. We plug in, we get 1 to the power of 4 minus 1 squared plus 2, and that is also 2. Because the two are identical, the function in between has the same limit by the Squeeze theorem. We want to prove that this is equal to 0. When you want to do that, you start with the expressions and you want to make up the whole thing. So you're starting with this and you say, I know sine, regardless of what the argument of log sine is, it's between -1 and 1. So sine is always between -1 and 1. Now, if I square that, it won't be that we square this one and this one becomes 1 and 1. This is 1, but this becomes in essence 0. That means because it becomes positive, okay? If I square it, sine becomes positive. 1 is always positive, and any number, sine could be 0, remember that. And 0 can make it 0. The fact that sine is between -1 and 0 and 1, therefore it's 0. And so I want to make it look like this. I'm going to add 1. I want to make it look like this. So let's add 1. So if I add 1 to all sides, I have what I want. This becomes 1 and this becomes a 2. Then I can multiply both sides by square root of x, and this is a positive value because x is approaching 0 from the right. Remember, when you have an inequality, if you multiply by any positive number, it remains unchanged. If it's negative, it flips over. The sign flips over, but we know it's positive because x is approaching 0 from the right. So we multiply by that, and now we have the expression that we were looking for. And now we are going to use the Squeeze theorem on the left side. On the right side, we take the limit of the left side as x approaches 0 from the right, and the right side as x approaches 0 from the right. In other words, I'm looking at this one here, this one here, and because both of them result in the same value, no matter what it is, it happened to be 0, but any value, because they are identical, by the Squeeze theorem, we prove that this is equal to 0. We want to find this limit. There are a couple of ways to do that. Let's go through the limit from the left and right. So as we approach x, as we approach -6 from the left and -6 from the right. So the numerator is 2 times x plus 6. We know that. And when x is from the left of -6, that means it's less than -6. This expression becomes negative. So minus of x plus 6, they cancel each other and they give us -2. On the other hand, if we approach it from the right of -6, that means a little bit larger than -6, like 5.9, then the absolute value simply drops. The numerator, we factor out the 2, and the 2 cancel each other, they give us 2. Because the 2 are not identical, the limit doesn't exist. They must be identical, and they are not. However, a different approach is to evaluate the expression and know that this expression is 2 when x is larger than or equal to -6, because you drop the absolute value, and it's -2 if x is less than -6. And with that approach, you get to the same answer. And I'm going to remind you why this is the case. Recall, the absolute value of x is x. If x is larger than or equal to 0, it's -x if x is less than 0. That's the reason. I hope everybody remembers that. We're going to look at the precise definition of limit. So I have set up the simplified version of that. This is read whatever, okay, it's a symbol in math, whatever epsilon larger than 0. This is read there is delta larger than 0, such that if the absolute value of x minus a is less than delta, then absolute value of f of x minus l is less than epsilon. So this limit means f of x is close to 5 when x is close to 3. That's really the bottom line. So we can make the value of f of x within an arbitrary distance from epsilon, distance epsilon from 5, by restricting the values of x to be within distance of delta from 3, but not equal to 3. If 3 minus sigma minus delta is x less than 3 plus delta, x can't be 3, then 5 minus epsilon is less than f of x less than 5 plus epsilon. In other words, this along the y-axis, the functional value is within epsilon of 5, in this case within delta. Precise definition of a limit says, let f of x be a function defined on some open interval. That contains a except possibly at a itself. We say the function has a limit at a, and the limit of f of x as x approaches a is L. If for every small number epsilon, epsilon is a small number, for any epsilon that is positive but it's small, there is some delta, there is a number delta, again, positive but small, such that the absolute value of x minus a is between 0 and delta, remember it's positive, then absolute value of f of x minus L is less than epsilon. However, we want to choose that number as small as we want to choose it, then there is a value such that the distance for x is delta, for L or f of x is epsilon. And what it really says, if a is here and we are within the vicinity of a by delta, that means a minus delta and a plus delta, it maps to f of x within L. That means L plus epsilon, L minus epsilon. That's the definition. So having said that, if you are looking at the following graph, such that the absolute value of x minus 3 is between 0 and delta, and absolute value of f of x minus 2 is less than 0.5, you can see this is number 3, we are close to number 3, and this is number 2, we are close to number 2 along the y-axis. And here's the definition that I like to use. Whatever the epsilon larger than 0, there is delta larger than 0. If absolute value of x minus a is less than delta, then f of x minus m is less than epsilon. So we always start with that, because whatever you choose for epsilon. And we know that the limit value is 2. And we put 0.5 here. And as you remember, in the case of an absolute value of x let's say k, and assuming k is positive, then x is sandwiched between minus k and k. So I hope everybody remembers that. So we can say f of x minus 2 is sandwiched between negative 0.5 and 5. So that is by definition of the absolute value here. And now we are going to add 2. And f of x is between 1.5 and 2.5, as you can see it along the y-axis right here. Graph, as you look at the graph, so according to the graph, x is somewhere between 2.6 and 3.8. This is what the graph tells us. So what is the delta? Delta is the minimum of the distance between these two. So take delta, the minimum of this distance, 3 minus 2.6, or 3.8 minus 3. Either this distance or this distance. And as you can see, the distance between these two is 0.4, right? Between these two, 3.8 minus 3 is 0.8. You always have to take the smaller of the two. In this case, the answer is 0.4. And any smaller number will do the job. Any smaller number will do the job. Guessing a value for delta given epsilon larger than 0, we need to find or guess delta larger than 0 such that if absolute value of x minus a is less than delta, then f of x minus l is less than epsilon. That is the process of precise definition. Now, in this example, we want to prove that the limit of f of x, in this case 4x minus 5 as x approaches 3 is 7. So we're going to start with this definition. And we notice a is 3. The limit is 7. We write that. We always start with this part, absolute value of f of x minus l, and we get to this part. When we find a relationship between epsilon and delta, practically we are done. So we are guessing a value. That's what we are trying to do. All right, so let's start with this. Becomes 4x minus 12. We can factor the 4 out, and that means I can divide both sides by 4, and absolute value of x minus 3 is less than epsilon over 4. So look at this one, and look at this one. If we put them next to each other, what does it mean? The choice of delta and the value of epsilon over 4, they go together. And so you should choose this one to be epsilon over 4. This is the main part, finding a relationship between the two. And now we start with this and we work our way back up to get to this one. So that's the choice. Proof showing that this delta works, reverse steps. We start with this. And since we have chosen delta to be epsilon over 4, let's multiply both sides by 4. And this becomes epsilon. We're multiplying by 4. Let's put the 4 in and we get 4x minus 12. So it becomes this. And then we rewrite it like this because we want to bring it back to that format. So this, simply when you put the 4 in, and this because we want to make it look like f of x minus l. And that is the proof. Therefore, what does it mean? What does it mean? It means if absolute value of x minus 3 is less than delta, therefore absolute value of 4x minus 5, which is f of x minus 7, is less than epsilon. So that's what we have proved. All right. And that's a graph showing that this is number 3, x is approaching 3. So within delta, along the x-axis, the y within 7 minus epsilon, and 7 plus epsilon along the y-axis when the limit is 7. So we have this distance. And bear in mind, this is for the illustration that they show a pretty large distance, but the distance is extremely small because both delta and epsilon are extremely small. So in this case, we said a function has a limit when the one-sided limits are the same. And we can do the direct substitution. Now, if the limit is equal to the functional value, then it is a continuous function at a. It is considered continuous from the right if the limit of f of x as x approaches a from the right is f of a, and continuous from the left is if the limit of f of x as x approaches a from the left is f of a. Also, we want to add a topic known as the intermediate value theorem. If f of x is a continuous function on the closed interval of a to b, and let n be any number between f of a and f of b, where the two values are not equal, there must exist a number c in a, b such that f of c equals n. This concept is normally used when we are dealing with a negative and positive, and we want to show the functional value also has a 0, which normally refers to roots of functions. We want to determine C such that this becomes a continuous function. A continuous function has this definition. So first, let's find the limit. And to find the limit, you have to look at where x is not equal to a, and this part we have to find the limit. If we plug in, we get 0 over 0. The technique is factoring. And the answer is 10. Now, if the limit is equal to f of a, then it's continuous at a. So what is f of a? F of a is given as c, and we have to make them equal. Therefore, c must be 10. That's the only way to make this work. F of x is sine x if x is less than pi over 4, and cosine x if it's larger than or equal to pi over 4. So we want to show the function is continuous from negative to positive infinity. I hope you know that sine and cosine, each one is continuous from negative to positive infinity. Therefore, this function is continuous everywhere except we have to check the endpoint at pi over 4. We are not too sure. So if it's continuous from negative infinity to pi over 4, union pi over 4 to infinity, let's check the endpoint by first finding the limit of f of x as x approaches pi over 4 from the left. Since this is less than, we are going to use this function for the left. And as you know, sine of pi over 4 is square root of 2 over 2. For pi over 4 from the right, since this has greater than, we're going to use this one. As you know, this is also square root of 2 over 2. And finally, we want the functional value at pi over 4. And because this has the equality, we use cosine x. And that is also equal to square root of 2 over 2. Because the limit exists as x approaches pi over 4, then if it's continuous at pi over 4, and since we already knew that it was continuous everywhere else, then it becomes continuous from negative to positive infinity. Again, this means continuous at pi over 4. And we are going to add this to this concept. That means it's continuous everywhere from negative to positive infinity. Use the intermediate value theorem to show there is a root for this equation, sine x equals x squared minus x between 2 and 3. And for this, we have to bring them to the same side, set it equal to 0. It doesn't matter which side. We can take everything to the right. And now we give it a name f of x. Now, this function is continuous. Why is that? This is a combination of a polynomial of degree 2. This is quadratic function, or you can say polynomial of degree 2, and this is a sine function. And sinusoidal functions are continuous from negative to positive infinity. Therefore, this function is continuous from negative to positive infinity, and that means it makes it continuous. Therefore, it's continuous. CTS, short for continuous. CTS. Continuous from 2 to 3 as well. And so, let's look at functional value at some points, and it has to be done by inspection because we really don't have a way of solving this except using calculators. If we choose x to be 1, if you choose x to be 1, this is 1, this is minus 1, they cancel each other. Minus sine of 1. Sine 1, that means 1 radian makes it negative. If you choose it to be 2. 2 squared is 4 minus 1 is 3 minus sine of 2. You don't even have to know what it is. Sine is between -1 and 1 makes this positive. So I want to make sure everybody understand what's going on here. So f of 1 makes it 1 minus 1 minus sine 1, which is minus sine 1, which is negative. F of 2, that was f of 1. F of 2 is 2 squared minus 2 minus sine 2. 2 squared is 4 minus 2. 2 minus sine 2. And how do we know this is positive? Sine, in worst case, is -1. So this will always be positive. Since 0 is between the two numbers, 0 is between a negative and, because this is a negative number and it's a positive number, then intermediate value theorem applies. IVT, intermediate value theorem, IVT, intermediate value theorem applies. F of x is continuous on 2 and 3 and has a root in between. That is the proof. All right. Limits at infinity, horizontal asymptotes. If the limit of f of x as x approaches negative infinity or positive infinity ends up being L, y equals f of x is a horizontal asymptote. We know the limit of 1 over x as x approaches infinity is 0 because the denominator is getting larger, and 1 over x to the power of p when p is larger than 0 also is 0. When you look at an exponential function, it's an exponential decay. The limit, for example, for e to the power minus x as x approaches infinity is 0, and that means y equals 0 is the horizontal asymptote, but as x approaches negative infinity, y blows up to infinity. If it's an exponential growth, it's the other way around. The limit of e to the power of x as x approaches negative infinity is 0, which is the horizontal asymptote, and as x goes to infinity, so does y. In this case, x goes to negative infinity, so does y. X goes to positive infinity, so does y. The concept of a vertical asymptote was discussed. If you take a limit of f of x as x approaches some number either from the left or right, and it blows up to negative or positive infinity, x equals a. A tan inverse is an example which has two horizontal asymptotes at x equals pi over 2, y equals pi over 2, and y equals negative pi over 2. So definition of a vertical asymptote is that the limit of f of x as x approaches a plus minus infinity, or a from the left or a from the right, then x equals a would be the asymptote. So those are some definitions. We want to find the limits, and I'm going to remind you, we've already done that. To find the limit, just plug in and observe. If it gives you a number, you're done. If it gives you 0 over any number other than 0 is 0. 0 over 1, 5.1, anything is 0, or 0 over -1 for that matter. A number over 0, you have to figure out if it's positive or negative infinity, and it can be indeterminate form if it's 0 over 0, infinity over infinity, or infinity minus infinity. Anytime you have a rational expression when the variable is approaching infinity, you divide by highest degree term in the denominator. And when you simplify, everything goes to 0, with the exception of 1 in the denominator. So this goes to 0, this goes to 0, this goes to 0, this one goes to 0, because t and t squared, they're going to infinity. So 0 over 1 is 0. In this case, t is approaching infinity, so we divide by highest degree term in the denominator, which is t. And when we simplify, this goes to 0, this goes to 0. So you have t plus 2 over -5, which is infinity plus 2 over -5. Now, infinity divided by any number is infinity. The only thing you want to pay attention to is the sign. Because we are dividing by a negative number is negative infinity. Other than that, if it's infinity divided by 10 or 10,000 or infinity to the second power or times 50 makes no difference, it's infinity. However, we always should pay attention to the sign. This, if you plug in, you get infinity minus infinity. The technique is to multiply and divide by the conjugate. This is a minus b, and this is a plus b, so we get a squared. That means it comes out as x squared plus 1 minus b squared is x squared. Therefore, x squared cancels out the x squared. And now when you plug in, the denominator is infinity plus infinity, so any number over infinity is 0. So it clearly becomes 0, which is not the case always. So infinity minus infinity can turn out to be infinity, can turn out to be a different number. All right, if we just plug in, and I want to discuss this, I want to make sure everybody understands e to the power of minus t, it means 1 over e to the power of t, and therefore when you plug in, you get 1 over e to the power of infinity, which is 0, okay? And it comes from the fact that a to the power of minus m is 1 over a to the power of m, b to the power of minus n is, let's make it 1 over b to the power. 1 over b to the power of minus n means b to the power of positive n. So you want to be careful with that. And this ends up being 12 over 4, which is 3. Part B is not a polynomial. However, we treat it as such because we have to divide by highest value in the denominator, which is e to the power of t. When we do that and we simplify, this is what we get. And this goes to 0, this goes to 0, and you end up with positive 1 over negative 3, which is negative 1/3. You plug in, you get infinity minus infinity. The technique is factoring. And now if you plug in, you do get infinity. So infinity minus infinity can be anything. That's why it's indeterminate. I can't emphasize this enough. All right, so let's cut it into 2 pieces. And I hope you realize this becomes 1 over e to the power of infinity, which is 0. And cosine, the limit of cosine, it oscillates, it does not exist. Therefore, dne does not exist. The first part goes to 0, the second part is the problem. For this one, again, it is not a rational expression, but we treat it as such because this goes to infinity. We divide by highest value in the denominator, which is e to the power of 3x. We divide everything by it. So let's see what happens when we do that. When we divide this one by this one, we get 1. When we divide this one by this one, we get 1. But when you divide this one by this one, I hope you realize you get e to the power of minus 6x. And this, because x goes to infinity, this goes to 0, this goes to 0. The answer is 1 over 1, which is 1. Limit of sine squared over x squared plus 1 as x approaches infinity. If you plug in infinity, the bottom becomes infinity and the top you don't know. But in general, I want you to know that sine and cosine, they oscillate. And the proof is using the Squeeze theorem. So let's look at the top and say sine is between -1 and 1. And when we square it, 1 becomes squared, but understand that also it's between 0 and 1. So this is 0, it won't go to 1. Otherwise, between 1 and 1, there is nothing there. Then we can multiply everything by 1 over x squared plus 1 or divide everything by x squared plus 1. Needless to say, this is positive, okay, class? Therefore, the sign doesn't flip over. So let's divide by x squared plus 1. 0 divided by x squared plus 1, and this is going to infinity. 0 divided by some huge number is 0. 1 over that. So by the Squares theorem, we take a limit of this one. As x goes to infinity, we know already it's 0. And we take the limit of this one as x goes to infinity, and this is also 0. You can work it out, or you can divide by x squared and find out. Therefore, the limit of the expression must be 0 by the squeeze theorem. Let's look at this expression, limit of tan inverse of ln x as x approaches 0 from the right. So let's put the 0 in. You can say tan inverse of the limit of ln x as x approaches 0 from the right, or you can put it in. It makes it, plug it in. This expression is negative infinity. And the reason why, I'm going to remind you of the graph of y equals ln x, and that makes it clear. So it's tan inverse of negative infinity, which is minus power 2. And as far as tangent, I hope you remember the graph of basic tangent. This is x equals negative power 2, and this is x equals power 2, just for the sake of one. In any event, let's look at the following, and we want to find the asymptotes. So to find the horizontal asymptotes, we take a limit as x goes to positive and negative infinity, and the best course of action is to divide by x squared. However, by now, because they have the same degree becomes 2/3. I'm going to discuss that in a moment. This becomes 2/3. And the vertical asymptote, you can simply set the denominator equal to 0. I'm going to assume we know factoring. So x becomes either 1/3 or -1. This one, you really have to go through the process. But if you wanted to do it fast, I'm going to remind you of how you found the horizontal asymptote in college algebra. If you have f of x equals a sub m x to the power of m, you continue indefinitely over b sub n x to the power of n indefinitely. Then if m is less than n, y equals 0 is your horizontal asymptote, right? If m equals n, y equals a sub m over b sub n. If m was equal to n plus 1, we would have oblique asymptote using long division. But in general, when m is larger than n, it goes to infinity. I want you to know that. So this is reminding you of what we have seen before. Let's go to the next question. Let me clean up the mess here. We want to find the formula for a function that has the following. Vertical asymptote x equals 1. So we have a denominator of x minus 1. Vertical asymptote of x equals 3. We must have x minus 3 in the denominator. Since horizontal asymptote y equals 1, assuming we don't have anything else, the bottom is x squared minus 4x plus 3. And because the horizontal asymptote is 1, the top must have the same degree, so we must have x squared. And since it's 1 and this is 1, we must have x squared at top. Again, this is one possibility. Is that the only one? Absolutely not. All right. I want to discuss this. This is the good old slope, and I'm going to write it as rise over run, y sub 2 over x sub 2 minus x sub 1. So if you look at this blue line, we have 2 points, and we find this slope. That blue line is called the secant line. Now, if I call this A, and if I call this X, gives me this formula. If I call this A and this distance of H, gives me this formula. If I call this A and this one B, gives me this formula. All of them are the same thing, rise over run, which is also known as DQ, difference quotient. Okay. Now, as we get Q closer and closer to P, we arrive at the tangent line. So f prime of A is the limit. Now take a limit of this one and let X approaches A, take a limit of this one and let H approaches 0. It's the same concept. And we come up with the answer here. It's important to know X. This is X plus H, or X sub 1 goes to X sub 2. However you want to put that, this is Y sub 1 equals F of X or F of X plus H. There are different ways of writing them. And the general format for F prime of X is the limit of F of X plus H minus F of X over H. But I want to show you this tangent line, which has Y minus F of A equals F prime of A times X minus A. There is nothing brand new about it. This is a point slope formula in algebra. Y minus Y1 equals M times X minus X sub 1. So you don't have to even memorize it. It's absolutely the same thing. We want to find the distance in feet of an object from a starting point, which is given by S of t equals 2t squared minus 5t plus 4d, where t is time in seconds. So part A is just elementary algebra, and that is basically saying that we want R, which is d over t, total distance over total time. And we use this formula to arrive at it. I'm going to assume everybody can plug in 4. Everybody can plug in 2. Evaluated, the answer is 7 feet per second. Again, bear in mind there are 2 points in time. They said instantaneous at 4 seconds, even if they don't mention instantaneous, but it's 1 point in time, that's what it means, and you have to take the derivative. And for now, we are using the definition where A is 4. And so we are going to plug in, and when we plug in, we get this one. And just quickly, this part, when you square it, becomes 16 plus 8h plus h squared. You multiply it by 2 and then minus 5, so on and so forth. And by the way, this 52, we can just bring it here. Okay. Now, number 32, number negative 20, 40 minus 52, they add up to 0. 16h and minus 5h, they add up to 11h. With 2h squared, we take the h out. And it becomes 11 feet per second. We want to find the equation of a tangent line at x equals 8. It is important for everybody to know we need 2 things. We need a pair and we need the slope. The pair in essence is given because all you have to do, put the 8 here. 3 times 8, 24 plus 1 is 25. The square root is 5. So we have the pair 8 comma 5. Let's find the slope. F prime of x. Let's go with dx and generalize it. The limit of f of x plus h minus f of x over h. So we are going to put x plus h instead of that and plug. Now, I hope you remember that if you plug in, obviously you end up with 0 over 0. That's what happens mainly in calculus. So the technique is the conjugate. We're going to multiply by the conjugate of this, which means we're going to change this to a plus. We're going to multiply and divide by it. So the answer is a squared minus b squared, which means each piece comes out. And what about the denominator? Don't ever touch it. Keep it intact, because the 0 in the denominator, namely h, is a problem. So notice in the numerator we get 3x plus 3h plus 1 minus 3x minus 1. So everything cancels out except 3h. And now the h drops. And now if I plug in, now I can plug in. And I hope you realize the first radical and the second one become the same, 3x plus 1. So this, when we plug in, becomes the square root of 3x plus 1. So we have 2 of them. And now, what is f prime of 8? If I plug in 8, I get 3 over 10. I want to make sure everybody understands what's happening here. If I plug in 8 here, I get 3 divided by 2 times square root of 3 times 8 is 24 plus 1 is 25. So that is 5. And the answer is 3 over 10. Also, if you plug in 8 into this, you get 5. So you have y minus y1 equals m times x minus x of 1. You do the job. Of course, this part is 3 over 10 times x minus 3 over 10 times 8, which is 12 over 5. Negative 5 moves and becomes positive 5. How do you add these two? 5 is 25 over 5. We get 13 over 5. By the way, you can always check as follows. Take a look. Since this pair belongs to the original function, it should satisfy the function. Since it belongs to the tangent line, it should satisfy that one. If you plug in 8, 3 times 8, 24 divided by 10 is 12 over 5, and 13 over 5 gives you 5. So check, make sure you have it right. The graph of a function f is given. Use it to sketch the graph of the derivative. So what you need to know is the following. Note relative max and mean f prime is 0. So at this point, this relative mean, relative max, f prime is 0, because if you were to draw a tangent line, it is a horizontal line. Every horizontal line has a slope 0. And when f prime is positive, f is increasing. So increasing means f prime is positive. Decreasing means f prime is negative. So first, at A, B, C, and never mind that we discussed that in a moment, the slope is 0 because you can draw a tangent line, and those are local extrema. So this corresponds to 0, this corresponds to 0, this corresponds to 0. So let's quickly draw this by hand, then I'll show you a better graph. So this one corresponds to 0. Again, we are graphing f prime of x. And this one corresponds to 0. Now, since this and this, they are decreasing, both cases, f prime is negative, which means for that part must be below the x-axis. Okay. This part, f prime is positive. This part, f prime is positive. So if it's positive here, it has to come back up, but it has to go back down to the 0. And over here is negative. It has to go below the x-axis. Below the x-axis. But it has to come back down, come back up to 0. And then after that is positive, becomes positive. And what matters is that how did they find this? They tried their best to go with rise over run. And if that is the case, then it corresponds to this point 5, y is 3/2. Let me clean up the mess. And this is how it looks like. So if we wanted to graph this one, then it is important to know that this and this correspond to 0. This portion increasing, f prime is positive, so it's above the x-axis. This portion decreasing, f prime is negative, below the x-axis, but has to come back up to another 0, right? There are 2 zeros. And over here, again, it's increasing, which means f prime is positive, so it goes above the x-axis. And those are the 2 points, and these are the graph, and this is a more precise graph of what we have seen. All right. How can a function fail to be differentiable when you have a sharp corner, a discontinuity, or a vertical tangent line? So I want to answer this for these questions. Obviously, this one at 0, we have a discontinuity. At number 3, we have a vertical tangent line. One may confuse this with a sharp corner. I'll explain it to you in a moment after we go over the second graph. This is clearly a discontinuity, and this is a sharp corner. So at -1 and +2. What I want you to notice, 2, it's sort of like a V shape, or maybe an upside down V shape. But this clearly seems to go all the way up from both sides. So there is really a difference between the two. If you can't distinguish among the two, that's fine. But it's really clear that this is like V shape, it's a sharp corner, whereas this one is going up. All right, the graph of the function is given. We want to use this to sketch the graph of the derivative. And so since there are line segments, if you assume this was a line continuing indefinitely, let's assume that was the case. All you had to do, find the slope, and then let's say the slope is 5, then y equals 5 is the answer. Okay, so I want everybody to understand this is line segment. So let's plug in the pairs, assuming this is -3, 1, -1, 0, 0, 1, so on and so forth. We can calculate the slope for all of them. I'm assuming everybody can calculate the slope. Simply put, you have this pair and this pair. Calculate the slope, which is rise over run. So 0 minus 1, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, and we get -1/2. By the way, this is the same, but in a positive direction. So this is a negative slope, this is a positive slope. These two easily, the slope is 1 and the slope is -1. So for this one, since the slope is -1/2, the line would be y equals -1/2. But there is a sharp corner here, so you have a hole and stops, and the same for the rest of them. So take a look at what happens here. And so we have the slopes. So y equals -1/2, for example, that would be a horizontal line going indefinitely if we had a line here. Since it stops here, right here we have a hole. Y equals 1, y equals 1/2, y equals -1, and we have 4 line segments. We want to find the following limits when x approaches -infinity. And it's important to pay attention to infinity versus -infinity. We can factor out, this is one way to do that, x to the power of 6, because we notice the degree of the denominator is 3. And before we divide by that, we can factor out x to the power of 6. And x to the power of 6 comes out either as x cubed or -x cubed. And because in this case, x is approaching -infinity, absolute value, the x squared is absolute value of x, therefore it's -x. And the same thing happens here. It comes out as -x cubed. If it was x to the power of 8, because 8 is an even number and comes out when you divide it by 2, 4 is even, then it doesn't make any difference. In other words, this is the case, but if it were x to the power of 4, it would be positive x squared, because when it comes out, it is still have an even exponent. So with that being the case, so this is the case, we take out -x cubed. Now we are going to divide by highest degree term in the denominator, namely by x cubed. So if I divide everything by x cubed, what happens? This goes away. This becomes 2 over x cubed. This becomes -1. Divide everything by x cubed. So now x is approaching -infinity. Under the radical, this goes to 0. You get 4. So under the radical, let me use a different color. Under the radical, you get -0 plus 4. This goes to 0. So the numerator is -2. The denominator is -1. The answer is 2. Now, this really is this. You can take it out now or later. You are dividing the top and the bottom by highest degree term in the denominator, which in essence is x squared. You are dividing by x squared. And it's important to know this. I can't emphasize this enough. And because of that, you can plug it in if you want. It doesn't make any difference. It remains positive. So this becomes 1. This one, if you take it in, and you can do that, this gives you 1 plus 1 over x to the power of 4 under the radical, which is simply 1. 1 over 1 becomes 1, and that's it.